Dear class, this is module 2, which is a very fundamental module in statics and physics. We talk about forces, vectors, how we can add them together, and later on this would be a capstone for fundamental of equation of equilibrium. I invite you to pay complete attention to this module, and if you feel I'm going a little too fast, please feel free to pause or rewind. In this module, we talk about forces, vectors, and operations on the vectors, and how we can add them when they are coplanar, collinear, or they are in a 3D space. Let's start with a very basic setup, which is a two-dimensional. We talk about also the Cartesian notation in two dimension. Let me start with a very basic quiz. Which of the following quantities are scalar? Force, position, mass, or velocity. Speaking about the scalar versus vector, we have two sets of quantities in physics and statics. One set, which are scalar, we can completely fully define them by one value, which is the magnitude of these scalars. Speed is an example. If I tell you I was driving 80 kilometers an hour, that is the speed. That is in a scalar. Or temperature, 37.5 degrees Celsius, or my mass is 77 kilograms. So all of these are scalars. There is no need for a more qualifier to fully define these quantities. But on the other hand, we have quantities that they are vectors. For example, velocity. Velocity is a vector quantity, and the reason is if I tell my velocity is 80 kilometers an hour, it's not sufficient, it's not fully defined. I have to tell you the direction, the alignment of the action. I have to tell my velocity is 80 kilometers an hour going from Vernon to Kelowna. That is a fully defined vector. You give the magnitude and then you define the line of the action, the direction. So among these quantities, obviously, the one that it is scalar is mass. Mass versus weight. So again, when I talk about the weight, weight is a vector. And I know outside of the physics, we have weight as a representation of the mass. When you go to grocery, you get 2 pounds of tomato. In a sense, you measure the weight, but you're referring to the mass. But in physics, when you talk about weight is a vector, and you will say my weight or the weight of this object is this much, and then you have to define the direction as well. We will talk about it in a little more detail later on. So next question, the vector addition, for vector addition you have to use which of these laws? So in a very basic scenario, you can simply use a geometrical representation and find the resultant of 2 or 3 vectors. One of the laws you are using is called the parallelogram, and if you're using Hibbler's textbook, it would be in page 21. I will talk about this in the next slide. So You might ask, why do we need to add vectors? I give you a simple example. So you have a pole or an antenna, and it's been anchored to the ground by something like a fork with four kind of fingers, and you do need to know what is the resultant of these force, because then you want to do a material selection on this bracket here. So you have one force here, one force here, one force here, and the fourth one goes here. So the resultant of all these forces would counter-react, so you do need to add them together. This is a very simple example of a situation in two-dimensional. You would like to add these forces together. A little bit of, again, basics. When you have a vector A, when you multiply an integer or a number by this vector, the only thing changes is the magnitude, or it could be the direction if the number is negative, but it doesn't change the line of action. If A is here, 2A, it's something that twice as A. Minus 1.5 A, the length is 1.5 times A, and direction going to the opposite direction. 0.5 A, or you divide A by 2, is the same direction, by the magnitude is half of the original A. That is correct every time you add a number, a scalar, by a vector. When you have two collinear vectors, so it means they are aligned the same line. So their positions is on the same alignment. Adding them is very simple. So you consider them almost as they are scalars. You add the magnitude of them. So in this case, A plus B, because they are all along each other's, so is R, and R has the same direction and alignment of A and B. So if you want to do A minus B, it's the same thing too. So in this case, A minus B perhaps is a vector like this, is A minus B. Because B is bigger than A, so the direction would be the opposite. But this doesn't happen very often in physics. So mostly we're dealing with vectors that they have different alignment, or they are in three-dimensional space. So let me introduce you a very simple law, which is called parallelogram law for adding two vectors. It's a very simple geometrical representation of adding two vectors, but often this is not the case in statics. Sometimes you have more than two. They are not coplanar, and they would be much more complex. So imagine you have vector A and vector B, and I want to add them together. So in this case, a simplest way is, so from the beginning of B, I make one vector equal to A, and then from here I make a parallel line and a parallel line here. And this diamond shape, you go the diagonal of that, and this is A plus B. I could very much do the same way from B. So if this is B, I make the vector A, B from beginning of the A. So this is A, this is B. And then I make parallel to B, parallel to A, and I can define this, which is A plus B. There is another method, it's called tip to toe. So if you have, for example, vector A, and you have vector B here, so from the end of A, you make a vector same as B, and then beginning of A to the end of B is A plus B, and this is B. What if you have 3 or 4? Then the same thing, you go from this is A, then this is B, and this is C, and this is D. Let me make one more, E. From the end of each you make the next one, and then beginning of the first to the end of the last, which is this, is the result on all these vectors. But this is not what we commonly practice in statics. There are much easier way to do this. So, which is the Cartesian notation. I will discuss that with you. So, a simple again parallelogram law. You have A, you have B, and then you make these two lines, and this is the resultant. However, this is not what we do in statics. In statics, in 2 or 3 dimensional, we start to give them coordinates, and we define unit vectors on these coordinates. We have x and y. X, usually we call it the unit vector I, and I is a vector with a length or magnitude of 1 on x direction. J is a vector with a magnitude of 1 on y direction. And simply, when you want to have these two added, so because there are 90-degree x and y, the equation is very simple. So it's square of x component plus x square of y component is the square of the length of these two vectors. So this is another representation. I have f, this f has 2 components. Fx is the x component of f, and fy is y component. So therefore f is equal to x component multiplied by the unit vector on x plus y component multiplied by unit vector on y. It is very commonly acceptable, depends on the problem. You can rotate these axes the way you want. So in this case, they are very straight. Sometimes you need to rotate them to make it easier. As long as these two are 90-degree, always x and y are 90-degree perpendicular to each other, the problem could be solved. We have 3 vectors, pretty much the same thing too. Now we have vector 1, 2, 3. Find all the x's, all the y's, and you add them. So when you do that, you have to be also cognizant of the direction. For example, it's clear that x component of f1, it's positive, so it goes like this, and x component of f2 is negative. So in this case, this is f1x, and this is f2x. So therefore, they kind of cancel, not quite cancel because they have different magnitude, but they kind of counteract each other. So therefore, x of f1 and x of f3 are positive, x of f2 is negative. With the same token, y of f1 and y of f2 are positive, and y of f3 is negative. So when you add them, so you have to go step by step. So first of all, you find the resultant of each component. So, and then all the x's and all the y's, and then you find the final x and final y, and we know that the magnitude of that final vector is the square of x component plus the square of y component and square root of that summation. So we will have a few examples here. This is exactly what we have here. So you can see that f1 xi, and we have f2x. Don't forget this is negative, the canceling, and f3. So these are all x's, these are all y's, and you find these two, and now you have the final x and fy. So this fr, and you want to know what is the direction. Obviously, in here, the tangent of this angle is this components, which is the y components of the resultant divided by x component. In a sense, the angle is tangent inverse of fy divided by fx, and I use the absolute value because this is, in this case, is positive. You have to be cognizant. If we are from 0, and maybe I make something like, let's just do it a little better. So something like this. So I go to here. So from 0 to 90 degree, if we have this angle, this is from 0 to 90 degree, both x and y are positive. This is the first quadrant. In the second quadrant, which the angle is this angle, let's call it theta prime. Obviously, the x is negative, the y is positive. When you are here in the third quadrant, and this is theta double prime, so you can see that both x and y are negative. When I'm here, and maybe I change the color, so here is theta triple prime. So here, this x component is positive, y component is negative. I encourage you to review this slide, then you completely understand what the angle should be. This is between 0 to 90, this is between 90 to 180, this is from 180 to 270, and from here is from 270 to 360. But when you use the absolute value, you always calculate from 0 to 90 value. Like for example, in this case here, if I have this and I have this one, so if I want to use the absolute value, it gives me this value, because it's absolute value of this divided by this. So the tangent of this angle, we call it alpha, so it's this absolute value by this absolute value. However, the actual angle from the positive x is this. So this is my actual theta, which in this case is 180 minus alpha. So we can calculate this alpha here. If I'm in this here, so now calculating x and y, so you see same thing. So this is my y and this is my x. So therefore when you do the tangent inverse of y divided by x, you are getting this angle, you see. So this is y divided by x, you get this angle, or you get this angle, the same thing. So in this case, if I calculate this value as alpha, and I want to calculate the actual angle between positive x, so it should be this angle, correct? So therefore, it's 180 plus alpha. So you get the whole thing because we calculated this alpha or this, which is this length divided by this length. Truly, the y and x in the third quadrant, as we explained, both of them are negative. I suggest students always use this formula here, the absolute value, and then by looking at the resultant x and y and their sign, they decide what quadrant they are. I'm sure you review this, spend more time. It's a very important concept. So let's start with a simple question. So the question is, I have three vectors, three forces, and I want to find the magnitude and the resultant of these three forces. As you notice, the forces are given in different kind of notation. So F1, obviously you have the magnitude and the angle it makes to the positive y. For F3, I have the magnitude, the angle it makes with the positive x. For the other one, I have the magnitude, and then it gives me this kind of triangle here, like this. 5, 12, 13, obviously, square of 5, 25 plus 145 is 169. So this is correct. But you might say, well, how do we calculate this? So obviously, you can simply calculate this angle, which is equal to this angle, and this angle is equal to tangent inverse of 5 divided by 12. You could simply say that it's also the cosine inverse of 12 divided by 13 or sine inverse of 5 divided by 13. So don't get confused by having different representation. It's pretty much the same. So what is the plan? Well, you find the resultant of these three vectors on x and y. You add all the x's, add all the y's, and you find the magnitude and the angle. Let's put this plan to work. Well, first one, F1, is very easy. So if this is 40 degree, this is 90 degree. So the x component is 15 kilonewton, either sine of 40 degree or cosine of 50 degree. We wrote here sine. And the y component is 15 cosine of this angle or sine of this angle. So it's pretty much the same. You realize that the sine of alpha is equal to the cosine of 90 degree minus alpha. So this is pretty much the same. So you have the x and y components of vector F1. Interestingly, you can see that the vector 1 is the first quadrant, so both of them are positive. Let's do F2. While F2, we could find the angle, but there is an easier way, is even without finding the angle, we can use this ratio, because x component of this force, which is negative and is here, is nothing but 12 divided by 13. The same ratio. Y component is 5 divided by 13. If you don't want that, you realize that 12 divided by 13 is cosine of this angle, and 5 divided by 13 is the sine of this angle. So we can use either way. So the value is negative 26 kilonewton, negative multiplied by the cosine of this angle, which is 12 divided by 13. The y is positive. This is the y. And the y is 5 divided by 13. So the final answer is this. X is negative, y is positive. And when it comes to the last one, so you realize that x is positive, y is negative. So you do the same thing too, 36 kilonewton cosine of 30 degree I minus 36 kilonewton sine of 30 degree. And this negative is because the y components here is negative. So now we broke down these three vectors to each of them to two components, x and y, which are perpendicular, and the rest is very easy. What do? We add all the x's, we add all the y's, and here is the final resultant. Now, by looking at these two values, both x and y are positive. Where are we? In which quadrant? Obviously the first quadrant, because both of them are positive. And in order to find the angle phi is tangent inverse of 3.49 divided by 16.82, and the answer is 11.7. So it should be fairly simple. I strongly encourage you to go back and review this lecture. You can find this particular problem. You can find several other problems that they can make this concept clear. So let's have another example. So we have a bracket with a hole, and there are three ropes or three forces applied. So we want to find the resultant of these three forces and obviously the angle. So same thing, F1, x positive, y negative. Just by looking at this, you realize that x component of this is obviously 4 divided by 5 multiplied by this value. The y component is 3 divided by 5 multiplied by this value. For this, 45 degrees is kind of tricky because I often don't give 45 to students because it doesn't matter, you sine or cosine are the same. So even the students make a mistake, the answer will be correct. But in this case, 45, so this angle is also 45. So therefore, the x component is 750 Newton cosine 45, except it is in negative direction. And the y component is 750 sine of 45 in a positive. And last but not least, for the F2 here, we see that the y is negative and the x is negative because we are in the third quadrant. And we can simply do the math by using the sine and cosine law. So start from the first one. As I explained, 4 divided by 5, 850I, minus 3 divided by 5, 850J Newton. This Newton multiplied by both these components. So this is the answer. For F2, using this 30 degree, so x is negative, y is negative. So if this is 30 degree, this is 60 degree, and we can use either the cosine of 60 or sine of 30, the same, minus 625 sine of 30 degree I minus 625 cosine of 30 degree J. And the last one, as I mentioned, is 750. X is negative, y is positive. And here is the actual resultant. So now we left with 3 resultant. You add all the I and then add all the J. And here will be the final resultant. By looking at these two values, both x and y are negative. Which quadrant are we in? Well, let's just go back. First quadrant, both of them are positive. Second quadrant, x is negative, y is positive. Third quadrant, both of them are negative. Fourth quadrant, x is positive, y is negative. So we are in the third quadrant. Okay, so now this is the vector here. So this is my x, this is my y. So if I calculate this angle, so just absolute value, this angle becomes 72.64. So what I did is tangent inverse of y divided by x. So calculate this, but truly you may need this angle, and this angle is 180 plus 72.64. If you use two significant figure here, the answer is 253. Let's have a simple quiz. I call it attention quiz. Here, resolve f along x and y and write it in vector forms. So here what we get. So we have F 80 Newton, and here is 30 degree. So if you want to use the same angle, F cosine 30 is y is going to be negative. So far this is correct. This is the y. X is 80 sine 30. So you can see that this is the correct answer. So this one is incorrect because both x and y are positive. This is incorrect, and among these two, answer C is the correct answer. Determine the magnitude of the resultant of F1 plus F2 force in Newton when F1 is this and F2 is this. Obviously, you want the magnitude, so you add x or I components, so 30, and then you add y components. So the resultant here, it's 30I plus 40J Newton. Now you want to find the magnitude is this square 90 plus this square 900 plus this square, which is 1600. Add them together, 2500. Square root of that is 50. So the correct answer is C. Now that we talk about two-dimensional Cartesian notation, we can expand it to a three-dimensional with this very same analogy. So when you are in 3D, which is most of the cases are, so you have an additional k component, which is the unit vector on z direction, and that's the only difference. So your vector has three components instead of two, but the analogy is the same. You add all the x's, all the y, all the z, and you can simply define the resultant. So let's just go a little further. A simple example, you have an airplane, and often when they want to anchor the airplane, so they have 2 or 3 cables connecting the wings to the ground, anchored to the ground. So you have to know what is the resultant of these forces on X, Y, Z in order to make sure due to the wind, this airplane would be steady. That's a simple example. So we talk about the addition and subtraction. Now the only difference here, now we have an extra k components here. So we can see that you add x's, you add y's, and you add z's, and at the end you have x, y, z. A plus b is ax plus bx, I, ay plus byj, az plus bzk. Or you want to have a minus b with the same analogy, you have these components. What if you have 5, 10 vectors? The same thing. All the x's together, all the y's together, all the z's together with respect to the sign, and then at the end you will get one vector with one x, one y, and one z. And that makes it significantly simpler than any other geometrical representation. So an interesting example here, you have this van and it's supposed to be lifted by a lift truck or a crane, and then you have these four forces, and hopefully they are equal because this should be in a balance. But what would be the magnitude of this? Obviously here we have four forces pulling this, and one force, which is the gravity of the van plus the plate, is pushing it down. So we have these forces. That would be one example. Another example is you have this tower, and this tower is been anchored by these three cables. The cables, the location has been specified. So we know what this point C or A or B are, and by knowing the location, we know this vector. So we have, and you want to find the vector, don't forget, this is something I would like to emphasize. So this vector, if I have the x, y, and z of the beginning of the vector, and I have x prime, y prime, and z prime of the end of the vector, the length of the vector is end I plus y j plus z minus z prime minus zk. So I have the xn minus x beginning I, yn minus y beginning j, zn minus z beginning k. That would be this vector. So you have all these three vectors, and then you have the magnitude of them. You find this vector, and then you find the unit vector, which we'll talk about it in a bit, and you multiply the unit vector by this length, you find this force. And so as you find the unit vector of this large vector and multiply by 400 Newton become that force, and so as for the 800 Newtons. So it's a very useful, it's a very simplified, easy to follow methodology, and I encourage you always do that, even for two-dimensional. So let's talk about the angles of the vector. So when you're in 2D, it's very simple. So you have these 2D and you have this vector, so you measure one angle. If it's 30 degrees, the other one is 90 minus 30. But when you are in a 3D, now you have three angles. Angle alpha, beta, gamma. Alpha is the angle the vector makes with the positive x. Beta is the angle the vector, blue vector, makes with the positive y, and gamma is the angle the vector makes with the positive z. So you have these three. It is very simple and we do, by the way, know that these are between 0 to 180 degrees. So that's one. So the first thing you should realize, and I magnify it here, alpha, beta, gamma. So alpha, or cosine of the alpha, is x component of the vector divided by a. Cosine of the beta is the y components of the vector divided by its magnitude, and cosine of the gamma is the z components of the vector divided by its magnitude. So these called direction cosine. Again, this is the simple equations you have here, alpha, beta, gamma, and these are the cosine or directional cosine. And needless to say, a square of this plus the square of this plus the square of this is equal to 1. And it's a very simple calculation. If I square that, become ax squared divided by a squared. And square of cosine beta is ay squared divided by a squared and az squared divided by a squared. So ax squared plus ay squared plus az squared, addition of them is equal to a squared, and the end is a squared divided by a squared, which is equal to 1. So simple proof of the formula, but don't forget the cosine of the angle with the x squared plus the cosine of the angle with y squared plus the cosine of the angle with the z squared, summation of them is equal to 1. This is a very important formula. That's one. And the next thing is, we talk about the unit vector here. Unit vector is a vector on the same direction with a magnitude of 1. If you remember, the unit vector on x is I, the unit vector on y is j, the unit vector on z is k. It's the same vector along x, but it has the magnitude of 1. So if you want to find the unit vector of any vector, all you need to do is you find the x component divided by the magnitude, multiplied by I. You find the y component divided by magnitude, multiplied by j. You divide it by the z components of the vector divided by the magnitude by k. And here is the formula. The unit vector of any vector is ax divided by ai, ay divided by aj, az divided by ak. Obviously, this is the vector has ijk. One more way, easier way to represent this is the unit vector of any vector is cosine of alpha I, cosine of the beta j, cosine of the gamma k, and you know alpha, beta, gamma, or the angle makes the vector with x, y, z. And you know that if you want to find the magnitude of this vector, you do x squared, y squared, z squared, and is equal to 1. So therefore, this is a unit vector because its magnitude is 1. So I would suggest maybe you review this slide. It's a very important concept because from here we go to dot products as well as to calculating the angle between two vectors, which is very important. Important notes. We talk about the direction cosine and how these angles define the unit vector of your desirable vector. So by having these three angles, and in fact you need only two of them, because we know that the square of them plus each other's the summation would be 1. And if you know the range, then you can simply find the third angle. So these angles can define the unit vector. And we know that the unit vector of any vector is cosine of alpha I plus cosine of beta j plus cosine of gamma k. Let's have an example here. So assuming that we have a vector, and here is the vector, so this is the I component, this is the j component, this is the k components. Obviously, you should be able to find the magnitude of this vector, which is equal to 1400 square root of that. So 30 squared is 900, sorry, 1400, yes. 20 squared is 400 and 10 squared is 100. So the answer is 1400 square root of that, which is 37.42. So you have this. And now if you want to find the unit vector of this vector, so all you need to do is you simply divide the unit vector of, so UF is equal to 10 divided by 37.42. I min minus 20 divided by 37.42j and plus 30 divided by 37.42k. So this is the unit vector, the magnitude is 37.42, and if you want to find the direction angles, so obviously this component is the cosine of inverse of the angle. So you simply write 10 divided by 37.42, and the cosine inverse of this value, which is 75.5 degree, and so as the other one. So you do have all the components, so you can have the magnitude as well as the direction angles, and you can have also the magnitude and the projection angles of this vector. So we will have a more complex question, and I will write it on the board to be more clear. Let's have another example. So we have two vectors. We have vector of f, as you can see here, and vector of g as in George. So now vector f makes 60 degree with the plane x, y, and the projection on xy has the angle of 45 degree with the x. That's one. And then the next thing is the vector g has the magnitude of 80, and alpha and beta are given. So alpha and beta are given. Obviously, in this case, you can also see that the gamma, which is the angle between this vector and z direction, is between 0 to 90 degree. Why? Because this is in the top hemisphere, it's not in the bottom. So the question is asking, find the resultant of this vector. Well, first of all, we have to find for each of these two vectors the Cartesian components x, y, z, and then add x, y, z of each. So let's talk about the first vector. Seems to be simple. So the first vector is vector number the f, which is 100 pound. So let's see what is the z components of this vector. If this angle is 60 degree, this angle is 30 degree, obviously the z components of f, which is fz, is 100 cosine 30. Right here. 100 cosine 30 or 100 sine 30 is pretty much the same. Next thing is I want to find this vector. This vector is a projection of vector f on the plane xy, and the answer is f cosine 60. So this is a red one. Now this red one, now we are in 2D, has two components. One is fx, this, and one is fy, this. So fx is f prime, which is the projection of f on xy plane, which is this value, multiplied by cosine of 45, and fy, which is to the opposite direction of the positive y. As you can see that this is positive x, positive z, and positive y. So the y component is the opposite direction of the positive y. So therefore, it's f prime sine of this angle to the negative. So this is my fy. So you see, we broke down f into f, x, y, and z. So we can simply write here is the Cartesian components of my f vector, x, y, z. That's good. The next step is I want to find the Cartesian components of my vector g. Well, first of all, let's calculate the angle gamma. the gamma is the angle that it makes with positive z. We know this formula, and we have this and this term, so simply we can calculate. So now, obviously, when you have here, so cosine gamma is equal to positive and negative of 1 minus cosine alpha square plus cosine beta square. So you have positive and negative, but however, as I explained in the previous slide, we go with the positive, or from 0 to 90 degree angle. So the correct value is this. The gamma, the angle is between 0 to 90, so it's 30 degree point 22. So now we have alpha, beta, gamma. What is the next step? We define the unit vector, which is cosine of alpha I, cosine of beta j, cosine of gamma k. This is the unit vector of vector g multiplied by its magnitude. This gives the actual vector g. So you calculate vector g, you have the vector f. All you do, you add them, x plus x prime, y plus y prime, and z plus z prime. And here is the actual resultant. So you add these two vectors, the one that we have previously and this one, and this is the resultant that we get. Let's have another question. Again, pretty much the same. Now, in this case, the question said that this is a screw eye object with two forces, so F1 and F2. So these forces, they are acting. So it's given the required information. Once again, you can see that for vector F1, we have the angle that it makes with the plane XY. We also have the angle the projection makes with Y. And then we also have the alpha, beta, and gamma. We have the magnitude pretty much same as the previous question. We can simply solve the problem. So here is f prime, here is f1z. F1z obviously is 300, the magnitude sine of 60 or cosine of 30. F prime, which is the projection of f1 on xy plane, is the magnitude cosine, and then now this is this magnitude, right? And if you want to find the y components, obviously you can see the y component is in this case positive, so it's 150 cosine of 45, and the x component is negative. So we have the positive y, negative x. So this would be my f1. So negative, positive, positive. Very much the same way that we did. So we have cosine of alpha I plus cosine of beta j plus cosine of gamma k. In this case, they're all given here. And multiply, this is the unit vector, this is the unit vector of vector f2 multiplied by its length or magnitude. This is the actual vector 2. Now we have two vectors. We add them simply x plus or I plus I, which is x plus x, and j plus j and k plus k. So this would be my final resultant. If I want to ask you what is the alpha, beta, gamma of the resultant, so in this case I have to find the magnitude, which is this square plus this square plus this square root of that, which is the magnitude, and then x divided by the magnitude. Cosine inverse of that would be alpha. This component divided by the magnitude, cosine and inverse of that would be beta, and z components divided by the magnitude of the vector. Cosine inverse of that would be gamma. As you can see here, these are the values. The magnitude is 481.7, and these are the values that we have. So you can see, because all of them are positive, the resultant has all positive angles, so between 0 to 90 degrees. So that's a little bit more complex than previous question. Now I want to introduce a very interesting concept. It's called dot products. Perhaps this is new, you haven't learned that in high school. It has lots of application, dot and cross products. For this particular module, we only cover the dot products, which is kind of less complicated, but in actual static, APSI 180, we will cover cross products of as well. So first of all, one of the most important application of dot products is when you have a vector and you want to find the projection of this vector in another direction. For example, if this is the force, and I want to know how much of this force will acting on this direction, then I have to use dot products. Very applicable, very practical, with lots of engineering application. There's another reason that you use dot products, and that is when you want to find the angle between two vectors. So sometimes it's not possible to go actually calculate that. All you need to do is you just find these two vectors, and you can use the dot products to calculate the angle between these two vectors. We'll cover both of them in next few slides. First thing, just to kind of like a reading quiz. So the dot products of two vectors P and Q is PQ cosine alpha, PQ sine alpha, PQ tangent, PQ secant. So the answer is this. When you have two vectors, the dot products of this vector on this or this vector on the other one is first vector, the magnitude, multiplied by the second vector magnitude, multiplied by the cosine of the angle between these two vectors. And in a sense is, when you do this, this is the actual projection of this vector on this direction. Next, dot products of two vectors, it's what? Is it scalar? Is it vector? Is it complex answer, or is zero? It could be zero, but not all the time. So obviously, let's go back to the definition. So a magnitude, which is a scalar, multiplied by another magnitude, which is a scalar. Cosine of the angle is a scalar. So 3 scalar, you multiply, the answer would be scalar. So the correct answer is a scalar. And this is unlike the cross products, which the answer of a cross product is a vector. In this case, the products of a dot products, the answer is a scalar. Okay. One of the applications we mentioned that you want to calculate the angle between these two cables. Very practical. Or I'm applying a force F. I want to know how much of this force would go along with this pipe, and how much of that goes perpendicular. So one force you apply from here has two components. How much of them goes along the pipe? How much of them is perpendicular? We know that the perpendicular is the one who can create a moment. We'll talk about it later. So two practical application. So vector A and B. So the presentation is A is a kind of bigger dot B. So, and this is a vector, this is a vector. The answer is A multiply, simple multiplication of two scalar quantity. A multiplied by B multiplied by cosine alpha. So obviously this is a scalar, so as this. This angle is obviously between 0 to 180. So this is now a larger angle. So you don't need to consider this angle, because if the vector is, for example, A is here, so instead of measuring this angle, you can simply measure this angle. So that's the way it is. So simply, we know that 2 pi minus alpha has the same cosine as the alpha. So it's in a scalar, as we mentioned. It could be a positive or negative number. And the units of the dot products will be the product of this multiplication. Now here is kind of tricky. If this vector is force, for example, and this vector is has different units, so the unit of the dot products, because it has this magnitude multiplied by this magnitude, it will be the multiplication of these two. So if we have Newton here, and here we have, I'm just saying that, for example, velocity, which is meter per second. So the answer of the dot products is the unit of the first multiplied by unit of the second. Obviously, the cosine. Okay, here is some terminology related to dot products. We know that dot products deal with two vectors and the cosine of the angle. Cosine of 90 degrees is 0. So whenever you have two perpendicular vectors, the dot products of them is 0. In a sense, if I want to know how much of this force applies in a perpendicular axis, the answer is 0. There is no projection. It's only a point. So therefore, having said that, I dot product J is 0. I dot products K is 0. J dot products K is 0. All of them are 0 because the angle is 90 degrees. And then you have, if two vectors are aligned on each other, or the angle is 0, the dot products of these two, it will be actually the first magnitude by the second magnitude, because the cosine of 0 is 1. So I dot I is 1. J dot J is 1. K dot K is 1. So now simply you have A dot products B. So here is A, here is B. So simply you do this multiplied by this, and then this multiplied by this, and then this multiplied by this. This has 9 components, of which 6 of them equal to 0, because they have the dot products of two perpendicular vectors. So the 3 of them only, they are parallel with a 0 angle, and the answer is AX BX plus AY BY plus AZ BZ. So it means X component multiplied by X component of the first vector multiplied by the X component of the second, plus Y component of first multiplied by Y component of the second, plus Z component of the first multiplied by Z component of the second. So the answer of a dot product is this: AX BX plus AY BY plus AZ BZ. And this obviously is in scalar, as this is a scalar. The unit is the unit of this multiplied by unit of this, whatever units there are. Now, let's see how we use the dot product to find the angle between two vectors. Very important. We have vector A, vector B, the angle is theta. I want to calculate the theta. So let's see. We have two definitions of dot products. First one is the magnitude of the first vector multiplied by the magnitude of second vector multiplied by cosine of the angle. And the other one is ax bx plus ay by plus az bz. So obviously we can simply find the cosine of the angle, which is a dot products b divided by the magnitude of a multiplied by the magnitude of b, and the theta is the cosine inverse of this value. I have an example which actually would help you to understand more. So here is the projection of a vector on two axes. So this components here is the dot products of A on A prime direction or alignment. So if I have this vector, I will find the dot products of this vector on this, which is this magnitude. This is the magnitude that we talk about, this, which is this term. But of course, you want to find the vector. This is the magnitude. Then you have to find the unit vector of A prime, which is U. And this is, it's called the parallel projection on this, the value here. So of course, the other one would be the perpendicular projection, which deal with the sine of this angle or cosine of this angle. This is 90 minus theta. Mostly we deal with the projection. When you want to find the projection of a vector on an alignment, you find the unit vector of that alignment, and then you simply find your vector multiplied by the cosine of the angle between your vector and that direction. This is a scalar, and you multiply a scalar by the unit vector of that direction. In this case, A prime. So we have two projections. So one is obviously the parallel projection, one is the perpendicular projection. If you want to find perpendicular projection, which is, this is the parallel projection, and this one is perpendicular projection. So obviously this vector, the magnitude of that is the square of this plus the square of this, square root of it. So simply you can find the magnitude of the perpendicular by squaring the magnitude of the actual vector minus squaring the magnitude of the parallel and square root of that. So in a sense, if you go back to the very first few slides that we have, so vector A is equal to parallel plus perpendicular. So you want to calculate the perpendicular is A minus the parallel. And that's completely understandable. So here we have, and this is what exactly we did. Remember that you have this vector, so you break it down to this vector and this vector. In a sense, if you want to add these two vectors, you go like this, you go like this, and this become your resultant. Called F1, this is F2. So in this case, if you have the resultant, then F1 becomes the parallel projection, and F2 is the perpendicular projection. Here is another interesting example. So we have two points A and B, and there is another I-hole bracket at point O. So there are three ropes here. We know that C is midpoint between A and B, and the geometry is given here. The question is asking what is the length of AB and the length of OC. Well, I think we can find the coordinate of point A. The coordinate point A is 0, 0, and 3. We can find the coordinate of point B. It's 4, 6, and 0. We know the vector AB means x of b minus x of a, y of b minus y of a, and z of b minus z of a. So it's simply 4i plus 6j minus 3k. That's what we have here. It's also another way to verify the answer is you think about this line. So we go from this point to this point, your z is reduced by 3 because the z of this point is 3, the z of this point is 0. So you came down 3 in vertical, you went 4 points on the x and 6 points on y, and that's the value. The next step is you calculate, you want to see the length of AB. Obviously, you have to find the magnitude of this vector, which is simply the addition of the square of each component, square root of that. So this is the length of AB as the first part. The second part is asking OC. Now, for finding OC, it's a little more complex because we don't know yet the point C. We could find it. If I have these two vectors, I go from O to A, OA, and then I have, maybe use different color, then I have AC. So OA plus AC is OC. If I have OA and AC, I can simply add them together and find the vector of OC. Let's follow that. We know that C is midpoint between A and B, therefore AC is half of AB. So anything we have here divided by 2, so it's 2i plus 3j minus 1.5 k, that's AC. And OA is very simple. Obviously, the OA, x and y, 0, it's only 3k. So the OA is 3k. So OC is equal to OA plus AC. So you have OA, which is this component, plus AC, which is we calculated here as this component AC. You add them, so this doesn't have I and J, so I is 2, J is 3, and K is 3 minus 1.5. So here is what we get. This is the vector OC, and now we need to find the magnitude of this vector, which is this is square plus this is square plus this is square root of that, which is equal to 3.91. I strongly encourage you to do this calculation by yourself and try to find the same answer. If you can, there is something perhaps wrong in your calculation. Here is another interesting example. We have this kind of hatch to the basement or to a place. It is held by a chain connected from point A to B. So the question is asking, determine the length of the chain AB and express the force of 50 pounds, which is applied to the direction of A to B in form of Cartesian components along AB. So let's just have a better look at this question. You can see, let's get to eraser. So okay, you can see this setup in a larger picture. So point A is here, point B is here, and we would like to know what is the distance between A to B. So geometrically we can calculate that, but we don't want to go that direction. We want to find the vector AB and find the magnitude of vector AB. And then when you have the vector AB, so you use the unit vector of AB, which has ij, k components, and then you multiply the unit vector by the magnitude of 50-pound force, and that will give you the component of force F on the direction of AB. A very practical question. Let's go step by step. Just gonna go and again erase these. Okay. There we go. So first, you have to find point A. So point A has obviously three components. It's in a space, x, y, z. So the direction of x is here. This is x. This is y. And this is z direction. So this point, the length of 5 multiplied by cosine of 40 degrees is the x. So the y component of this is actually 8, because this door pivot, it doesn't matter what is the angle, it's always going to be the 8, the y component. And if this is 40 degree, the other side is 50 degree, so the z component is 5 cosine 50 or 5 sine 40. So these values are exactly here. So we have the point A. So next thing is you find point B, obviously. Point B is very simple. So the x component is 0. There's no x. The y component is 5. And the z component is 12. So we know that how we calculate a vector when you have the beginning and the end is x of the end minus the x of the beginning. That's the x component of the vector. Y of the end minus the y of the beginning. That's the y component of the vector. And the z components of the end minus the z components of the beginning is the z components of the vector. Having said that, we can simply calculate the vector AB, and these are the Cartesian components of that. So how do you calculate the length of the vector? So it's very simple. So the formula is x component squared plus y component squared plus z component squared, square root of that, and is approximately 10 feet. That's the part 1 in this question. The part 2, as I mentioned, you go and calculate the unit vector, and you know that for calculating unit vector, the easiest way is you divide each x, y, z components by the magnitudes, and you have ijk, which is a vector with the length of 1. This is what we get here. And you multiply this by the 50-pound vector. So these are x, y, z components, and you multiply it by 50, and this is eventually, you get the xyz component of the force of the 50-pound applied by this chain on the direction of A to B. Again, a very interesting question. When you are learning the statics, you do have to have a good sense of geometry and trigonometry. You will develop that set of skills. Okay. And last but not least, I believe the question is asking to determine the coordinate direction angles or direction cosines. So alpha is this component. So the angle is 112 degrees. Beta is this component, still is negative. It means that it's more than 90 degrees. And gamma is positive, is the angle that AB makes with the positive z direction is 29 degrees. I allow you to look at this for a couple of minutes. Again, it all goes to calculating the point A, the coordinates of point A, and the coordinates of point B, and from there you find the vector AB. From the vector AB, you find the magnitude of vector AB. Then you find the unit vector of AB by dividing vector AB by its magnitude, and then you multiply that by the magnitude of 50 pound, the force F. And for the direction cosine, all you need to do, you go back to unit vector, and I component is the cosine alpha, J component is cosine beta, and K component is cosine gamma. Let's have another question here. So another interesting question. So we have another setup here. So we have point O, which is the coordinates. We have this rod from O to A, and we have this position. Right away, you have to be able to define this position. This position, the Z is -1, the X is 2, and the Y is 2. Okay, you have the force F, 2J plus 4J, 2I plus 4J minus plus 10K kilonewton, and the question is asking what is the angle between the force and this rod. So what do you think? What would be the strategy in this question? What is the best way to find the angle between two vectors? Let's go back to one of the application of dot product. So dot products, one application was you find the projection of one vector on the other direction. The second one was finding the angle between two vectors. So let me just get this written on here. So we know that the dot products of A, B is equal to magnitude of A multiplied by magnitude of B multiplied by the cosine angle between A and B. That's 1. On the other hand, we know that A dot products B is equal to AX BX plus AY BY plus AZ BZ. And you realize that this is a scalar number. The unit is the unit of these two numbers. So if I want to find the cosine of alpha, which is the angle between these two vectors, obviously the simplest way is you have this term, which is A dot products B, divided by the magnitude of A by the magnitude of B. And obviously, they have the same unit. As a result, the cosine does not have any unit. So let's get back to the calculation. So we know that the cosine of the angle is equal to the dot products of these two vectors divided by the magnitude of each of them. So it's pretty simple. So first you find the vector OA. So this is the OA, as I mentioned, that 2, 2 minus 1. This is the magnitude. You find the force already given. This is the magnitude. And then the next step would be the dot products of these two, which is I, J, J, K, K. This is, and you notice the unit is 2 kilonewton meter. This is meter. This is kilonewton. In a sense, this is work or energy. So force multiplied by the distance. So you have this value. What do you think the next will be? Well, obviously the next would be this value, which is the dot products, divided by the multiplication of this by this. So let's put it into work. So as 2 divided by 10.95 multiplied by 3, and the cosine inverse of that, so this angle ends up to be 86.5 degree, which is very small angle, close to perpendicular. Another interesting question, I strongly suggest you to review that if you want to pause or rewind. So then we go to the next question, which is a little bit more advanced. What else do we need here? So if it asks also to calculate the unit vector of these two, and we did that. It was needed the angle. Now unit vector of OA is vector OA divided by the magnitude. Here's the unit vector. And then you also have force. You want to see, the question also asking what is the projection of this, the second part I believe, the projection of this force on this direction. So remember that the second application of the dot product is you find the projection of a force on a direction. So now you have the unit vector of OA, and then you do the dot products of the force F by the unit vector of OA. And here, that's what we did. Force multiplied by unit vector of OA. So you have the OA, you have the force, and the answer is 0.667. So now, something interesting. You see, because of the very large angle that you have, the angle between these two is about 86 degrees. It's quite large, closer to perpendicular. The force is about 11 kilonewton, 10.95. But because of the angle, only about 0.7 kilonewton, a fraction of the force is applied to this rock. Obviously, if this was 90 degrees, the answer would have been 0. If this would have been 0 degree, the answer would have been 10.95. That shows the larger the angle is closer to 90 degrees, the less force would be applied, and that's common sense. If you want to push a table, you always want to be parallel to the table to apply the most force. If you are pressing perpendicular, you never push the table forward. So statics always makes sense. It's a very simple law of nature. So good question. So I highly encourage you to review this question. Now here comes a review again, the dot products of two vectors. So you can find it. So finding the angle, that's what we did that here, the cosine inverse of the dot products divided by the magnitude of each. Here is an interesting problem I presented at the end of this module because it covers almost everything that we went through. The problem is given two vectors, vector A, form of Cartesian components, and vector B in forms of the magnitude and two angles. The third angle is defined between 0 to 90 degrees. And the question is asking what is the angle between these two vectors. So I need to go over the board to write this question down. So what we have here is obviously two vectors. So vector A, so minus 2i plus 3j minus 2k kilonewton, and vector B, which has 3 kilonewton, the magnitude. Alpha, the angle makes with x is 60. Beta, the angle makes with y is 45. Gamma is not given, but the range is given between 0 to 90 degrees. So what is the first thing we do? Obviously, we do need to define the vector b. So vector b, the angle is not given. So we know the formula is cosine alpha squared plus cosine beta squared plus cosine gamma squared is equal to 1. Any vector. So from here, we know that cosine gamma is equal to plus minus 1 minus cosine alpha squared plus cosine beta squared. And from here, we can calculate. So plus or minus. So 1 minus 60 degree cosine of 60 is 0.5, so the square of that 0.25. Cosine 45 degree is 0.707. Square of that is 0.5. And this answer right here is plus minus 0.25. So you might get two answers here for the cosine. This is from 0.5 or minus 0.5. Because it's given here the range, so we definitely do not accept this one. So this is the correct answer, and from here we can conclude that gamma is equal to cosine inverse of 0.5, which is 60 degrees. There we go. So we have gamma 60 degrees. Now we can simply write the Cartesian components form of vector b, which is 3, the magnitude, multiplied by the unit vector. What is the unit vector of vector b? Is the direction cosine. Is 0.5 I plus 0.707. Bear in mind this is the cosine of 45 degrees plus 0.5k. And now you can simply write this one, b is equal to 1.5, and this is equivalent to I plus 2.121 j plus 1.5 k millimeters. Now we have two vectors. Get back to the previous question. So in the previous question, we saw that we have two vectors with two sets of Cartesian components. You want to find the angle between these two vectors. Remember what was the analogy? The analogy was we do the dot products, xx prime plus yy prime plus zz prime. That is the dot products. And then you have the magnitude of these vectors. You divide the dot products by the magnitude of the vectors, and the result is the cosine of the angle between these two vectors. So, let's continue. So, the cosine of, I'll call it phi, which is the angle between A and B, is equal to, so this multiplied by this x prime, zz prime, and y prime. So it's going to be minus 3 plus 6.363 minus 3, and this is divided by the magnitude of these two vectors, which is 4.123 multiplied by 3 is 0.363 divided by 12.369, and this is 0.051. So the next page, the cosine of the angle is 0.051, and you can simply calculate the angle between these two. I like to leave it to you to get to this point, and then you can find the answer. I'll give you the answer at the end of this module. So let me recap what we gone through as far as defining a vector is concerned. There are several ways to fully define a vector. And to start with, when someone gives it to you in a silver plate, is when you have the Cartesian components of the vector. You have I, j, k. So you have the magnitude, you have the cosine direction, you have everything. Unfortunately, it doesn't happen unless in a perfect world. So often we don't have the luxury of having everything. You know, you have a table. How could you find these values right off hand? The next is you have the magnitude of the force, and you have direction cosines. You have two angles, and from two angles you can find the third angle, and then you can define the unit vector, which is cosine alpha I plus cosine beta j plus cosine gamma k, and then you multiply by magnitude, you get to the same point as we were here. You go to this point. Okay? So imagine you have a vector of 200, and these are two angles. So find the third angle, same as the previous question, and then you can fully define the vector. The next is you have the magnitude of the vector, and same as a couple of questions you have the angle with the z direction, and then you have the projection angle on xy plane. If you recall, with these two angles, these are different than the other angles. One angle is gamma, the angle it makes with z, and the other angle is the angle the projection makes. And if you also want to remind you, if this is like this, so you have this angle, and then you have this projection, this angle. So this is x, y, z. So you have these. This is gamma, and this is theta. In this case, obviously, you still can find the z components, which is the magnitude multiplied by the cosine of gamma, and then here, so this angle is 90 minus gamma, then you have this length, which we call it f prime, and f prime cosine theta is x, and f prime sine theta is the y. So still you have x, y, z components, then you get back to the same form. If you have the magnitude and unit vector, it's second easiest because you multiply the magnitude by the unit vector, and that would be the answer. So, for example, if I know that this is 2 kilonewton and this is what I have. By the way, I didn't give you the z, but you can find the z easily because this square plus this square should be plus this square should be 1. So 1 minus this square plus this square, you can give you the z. And last but not least is when you have 2 points that are aligned with the force, the line of action, you have 2 points, and then you have the magnitude. From 2 points, you find the vector of that 2 points. Vector passing from, let's say, A to B. From that point, you get the unit vector of AB, and then it will go back to the previous case. So you have the unit vector of the vector and the magnitude. In any of these 4 scenarios, the vector is fully defined. You should be very comfortable doing any of these 4. This is the end of the module 2. I strongly encourage you when you want, like if you cannot keep up, go a little faster than usual, so you can rewind, you can pause, you can, think about the concept to reflect. But I really like you completely understand this chapter, because the next module would completely rely and based on your understanding of this module. Okay, as I promised you, I want to give you the answer of this question. It was an interesting problem. I certainly hope everyone went through a step-by-step to get the final answer of the cosine of the angle is 0.051. And obviously, if you're this far, perhaps you all got the answer of 87 degrees. The angle between these two vectors are 87.1. Please review this chapter as many times as you have to fully comprehend and understand. This is a very fundamental chapter. I taught statics for several years, and I often observe when students feel a little lost in more advanced concept. It's not because they didn't understand that concept, it's because they didn't understand the more fundamental concept, including the vector and how you represent the vector. Please make sure before you go to next module, module 3, you review this chapter, take the quiz, and I am confident if you fully understand these 3 modules, you will have absolutely no problem in statics and hopefully in dynamics too. So don't panic. Go organic, and see you in the next module.